In this video, I'll describe a more efficient method for computing interval estimates. To do this, we'll use a scenario we've seen in previous videos. When you visit your local ice cream shop, you'd like to get 1 scoop of chocolate ice cream. With the help of your friends, you order and weigh a total of 28 scoops of ice cream. You compute the average weight of the scoops and get 4.6 ounces. You want to know, what is the average weight of all scoops at the shop? The way to answer this question is to construct a confidence interval for the parameter. Previously, the way you would construct an interval estimate is to make numerous hypotheses about the parameter, such as hypothesizing that the mean weight is 3.5 ounces, or 4 ounces, or 4.3 ounces, or any other number of ounces. And then you'd make a model for each hypothesis and simulate repeating the study to determine which hypothesis is an observed statistic of 4.6 ounces evidence against. Essentially, this was a guess and check method. So first, we made a model for a parameter of 3.5 ounces. We looked at the sampling distribution and saw that there was a p-value of roughly 0. Then we made a model for a parameter of 4 ounces, looked at the sampling distribution and saw that there was a p-value of 0.4%. Then, for a parameter of 4.2 ounces, the sampling distribution gave us a p-value of roughly 5%. And for a parameter of 4.3 ounces, the sampling distribution gave us a p-value of 14.4%. We figured out that any parameter between 4.2 and up to 4.6 ounces would make a statistic of 4.6 ounces get a p-value of at least 5%. So this 4.2 distribution was special. Let's take a closer look at it. In this distribution, the observed statistic of 4.6 has a p-value of 5%. In particular, the observed statistic basically cut off the upper 2.5% of the values in the sampling distribution. So in this process of guessing parameter values, our goal is to find a parameter that would put the observed statistic at the 2.5% upper cutoff of the resulting sampling distribution. This would be true for any parameter that is within this distance of the observed statistic. So another way to think about our goal is to find this distance. Is there a way to do this without doing all of the guessing? One thing you might have noticed is that all of these sampling distributions have the same shape and spread. So if we looked at the sampling distribution generated by the original data, it would also have the same shape and spread. And if we looked at the upper 2.5% of this sampling distribution, the distance from its center to the upper 2.5% cutoff would be the same as in the distribution centered at 4.2. In other words, if we took the sampling distribution we generated from our original data and shifted it down by the distance from its center to the upper 2.5%, we would know the smallest parameter value that would put the observed statistic right at the upper 2.5% cutoff. And similarly, we could find the distance from the observed statistic to the lower 2.5% of the sampling distribution generated from our original data. And if we shifted it up by this distance, we'd get the largest parameter value that would put the observed statistic at the lower 2.5% cutoff. So let's summarize what we've seen here. Our goal was to find all of the parameter values that would give a p-value of at least 5% for the observed statistic. Equivalently, we could find all of the parameter values that would put the observed statistic at the upper 2.5% and lower 2.5% cutoff for the sampling distribution that generate. Using the fact that all of the sampling distributions would have the same shape and spread, we could use what's called a bootstrap sampling distribution, which is where we use the original data as a model for the population, and then look at the upper and lower 2.5% of the simulated statistics. And all of the values between these cutoffs would be parameter values that would give a p-value of greater than 5% for the observed statistic. In other words, a 95% confidence interval for the parameter.